I'm not great, so no training.
Okay, hi. We should be now streaming audio. Okay, let's start. So, hi, my name is Philip, and today we are in the office in Sofia, Bulgaria. I'm here with my colleagues, and today I will talk about blockchain and cryptocurrencies. So first, a little bit about me. I studied computer science. I have a master's degree in the Vienna University of Technology. I worked in deep learning, in face recognition in Moscow for a couple of months previously, and there I also co-organized the Ethereum meetup together with some friends, and it really grew very fast. I've been advising on one academic thesis about blockchain already, and recently we launched Coin Market Launch, which is a company that helps promote ICOs and also helps them consulting, figure out everything what they need, and also connecting, which is the second project we are working on, which is a decentralized peer-to-peer exchange. But okay, so let's start to tell you guys a bit about Bitcoin and the blockchain, and it's always good to start with the history. So in 1992, Dwor and Naor, they proposed proof of work for the first time. So this was basically the first time someone said that, okay, in order that you prove that you did something, like let's use computing power, right? Because before that they had some problems. The internet forums started to come up, and they had spammers there, and you have some checks of how you can check if someone is spamming. But if they have to use computing power, they can only spam so much because they have some economic cost for that. So by the way, you can always ask questions either on the stream or also here at the office. So when you don't understand something or didn't hear it, then please just ask, okay? So yeah, they did this in 1992 actually. In 1998 the first cryptocurrency kind of was invented, but it has had still severe drawbacks, and well, we know that it didn't come to life really fruitful because of these drawbacks. But in 2008 then Bitcoin, the first white paper about Bitcoin was presented by Satoshi Nakamoto. Have you heard about him actually, or yeah? So it's not really clear who he is, where he is. There are some speculations, but we just know that either was a group of people, most likely some people believe that, because he really researched on this topic for a long time, and he came up with a lot of good ideas. So either he was a genius who doesn't want to get known and used a pseudonym, or it was a group of people. Anyway, I have my own theory about that. And my theory is that because Satoshi Nakamoto actually owns a large amount of bitcoins, I think it's like $5 billion worth or so now, but they still haven't been touched yet. And so my theory is that he lost his private key, which he needs to transfer them. He just doesn't want other people to know who he is because he's so ashamed. Yeah. No, but who knows? So we will maybe never find out, maybe in a couple of years. And 2013 then Ethereum came along, which in my opinion is a really big upgrade to the Bitcoin protocol. Some other people disagree, but we will get to that in detail a bit later. Then here I put 2016 ICOs. There were some ICOs before, so ICO stands for initial coin offering. But in 2016 is when this boom really kicked off, and now in 2017 we will talk about this a bit later also. It really exploded. Okay, so because everybody likes math, right? Let's do some math. Okay, let's change that, otherwise you cannot see so much. Thanks for the hint. I will just make my image a little bit smaller, so yeah, you guys can see me much better, I hope. Okay, let's try if that worked out here. So, but anyway, first some math, because everybody likes math, right? And I think you're all eager to learn something more about math in general. So today you can do that, and we will apply it to the blockchain later on. But I think you can agree that we don't need the details, right? Maybe it will be taking too long and it will be like more a university lecture then. But again, so if you have questions, please ask, because I'm here that you learn something, and otherwise it's not a good use of our time. Okay, so first off, let's start with private and public key cryptography. Have any of you heard about that?
Yeah.
Yeah? So are you familiar with the concepts there?
Yeah.
All of you, Nicola?
I'm not really that familiar with
Okay.
blockchain.
Good. So I will explain it, of course. So basically there is some kind of encryption, right? When we want to transfer a message secretly, we have to encrypt it, or so that other people cannot read it, obviously. What we could do is we could agree on a key, like you and me, Nicola, and we both know this key, and then we use it to encrypt the message, like I encrypted with the key and you decrypted with the same key. But that has the problem that you can now share this key with other people, and I don't really know who else can read it, right? Or if other people find out, it's a big problem, because somehow it's between us, and I have to trust you that you don't share it. So that's also why private public key a big advantage, a big plus to that. So they were invented a bit later, and there is a key pair always. So there's one public key and one private key, and they always belong together. And the private key, like you keep private, you only keep it to yourself, you never share it with anyone. And the public key you can make known to everybody in the world who needs to know it, or it doesn't matter, you can just post it on your website and then other people can use it. I will tell you a bit later why is that the case, okay? So how do we create these public and private keys? Basically it's math again, some algorithms. But you start always off with the same thing. It's like a random number, a very large random number. Let me just make that even a bit smaller here. Anyway, I think people are not so interested in me, but rather in the content I provide.
What about the random number? How random is it?
So yeah, random number, it's a good question. So ideally, we would like to have real random numbers, so that we can never predict in any case when we create, like click a button, create random number, which will come. In practice, this is very difficult, because for true randomness, you always need some source of randomness, right? So what is used in computers is either time or some hardware fluctuations. So some people use even the temperature of the hardware, because it fluctuates by sometimes a bit more, sometimes a bit less. And basically it's difficult for other people, like if I have a hacker somewhere in Russia, it's difficult for him to know all these parameters, and that's why we say, okay, it's random, it's good enough, but they're basically called pseudo-random numbers, because they're not really random, but they're good enough, so the cryptography really holds.
What about in the protocol itself, in Bitcoin? All the peers using the same random generation principles?
So actually it's also a good question, it's very technical. So for Windows and for Linux, usually there are like random libraries which take care of generating random numbers. And also there's like some system calls from Linux, for example, from Windows, where you can really have also them call these system calls, they call hardware random seeds or so, There's actually also a project or multiple projects in the world which want to provide random numbers as a source, or just some randomness, true randomness. So some people use the decay of cosmic rays. Yeah, you heard about it? So like the cosmic rays that come down, and it's like that. Yeah, you cannot really predict them, so it's random. Some people, they also have lava lamps. There's actually one project where a camera there's a wall of lava lamps, you know them, that like get hot and then it bubbles up and goes down, it's cold.
Okay.
Want a wall of, I think, 50 lava lamps and film with a camera, and from that they produce a random input.
Right.
But yeah, it's really important.
But does that, so does the security depend on the method that you generate it on? It obviously does, but my point is, so there is not an agreement what all the peers are using as random generators.
No.
So you can actually create your public and private key with some not so effective random generation, and you can be susceptible to actually to attack.
Exactly.
Okay.
So yeah, so the question was if all peers are using the same random generator, and the answer is not necessarily. They just have to use a random number generator to then obtain the public and private key. But the really important thing is what these random numbers, it obliges to like each one of them. And you're right, if there's a weak random number generator, then this can be exploited to predict the keys. Actually, this is also the case in some hardware routers or so, old ones from Cisco. I think there was recently something where they used a very weak random generator, which always started with the same number of sequence. It generated random numbers, but when you restart it, it always produces the same random numbers again. And then, of course, if you once know the seed, the start sequence, and then you know a whole sequence, and you can predict. So all these attacks actually on security, most of them are by exploiting either weak random numbers generator or just weaknesses in the protocol.
Basically, that's how authenticators work, right?
Authenticators, you mean the Google authenticator?
Whatever, every authenticator works that way.
Well, yeah, so there is some random seed.
If you know, for example, the code in a certain minute, and you know the code in some other minute, and you know the exact time that this code was produced, you can actually reverse the whole cycle and see what the script for the crypto.
Exactly. So I mean, not all. So there's different protocols between them, but there are some that for 5 minutes, if you know, like for 5 minutes you can predict it, but then they change the seed.
Yeah.
So but yeah, of course. Okay, but let's try to continue. Okay, this is very broken. Nice. So anyway, if you want to encrypt a message, what is important is that like in cryptography, we always talk about Bob and Alice. It's the two participants in who want to exchange messages, Alice and Bob, A and B. If Bob wants to send a secret message now to Alice, Bob takes the message, encrypts the message with the private key, the public key of Alice, sends it to Alice, and Alice can decrypt it with the private key. Is that clear?
Mm-hmm.
So there's, by encryption, just think of there's some random, there's some complicated function applied or some complicated code that uses the message as input and this public key and produces the encrypted message which no one else can read except for Alice. Then we have signatures, so basically that's the other way around. If Alice, so we have sometimes this problem that I get a message, for example, in email, and I don't know who it is coming from, or I know that the sender, maybe the email address, I can see it, and I trust that if the email address is from a person I know, then the message is from him. But actually this can be in some cases faked, and so for me to know that a message really comes from someone, this person, in our case again Alice sends a message back to Bob. Alice can sign this message with her own private key, and if I have the public key of Alice, if I know it because it's publicly known, I can download it from her website, then I can check that this message is really from her and only from her, because it's only she knows the private key, and as we know, the public key and private key are connected, right? And so this is a really important property, that I can verify that the message is from him and only from him. And this will be also very important for the blockchain later, how it works, because we basically don't have to trust that the message is from you, but we trust in the signature, the math, that the message is from you. So basically, there's no trust involved because math it doesn't work on beliefs; it works on rules and logic. Okay. Any more questions? Okay, so let's come to hashing. It's another concept. I know it's a bit dry, but you will understand why I explain them a bit later because they all are needed then as blocks for make the whole blockchain work. So hashing, in principle, is a complicated function, okay? But this function, it has some properties. Just think of that if you have some input, let's say you can have a text or a number, then you apply this function and you get an output. And the output now is always of the same length. So even if the input is either, I don't know, one number or a page from a book or a whole book, the output is always like, it can be 20 characters or 60, but it's always the same length, and that's important. And the second really important attribute of this is that when I know the output, so when I know the hash it's called, I cannot determine what was the input. So when I have the input and the function, it's very easy to compute the output, it's very cheap, it's very fast. But when I have the output, for me to know what the input was, I have to try all combinations of the input or all inputs that are possible in the universe, basically, because that's how that's how these functions are designed. And now some of you might ask, okay, maybe I can have two inputs with the same output. Yes, that's possible, but it's extremely unlikely. So this all I would say math or this all rules, they're based on statistics a bit, because for me to find two inputs which produce the same output, which is called actually a hash collision, I have to try so many combinations that the probability of this is so small. So I don't know, to give a comparison, it's probably 1 divided by the atoms in the universe, or it's 0.0020 more zeros 1%. I don't know the exact number now, but it's so extremely small that I would need to use all the computing power in the world for a couple of thousands of years doing only this to find one collision.
What about when quantum computing is well devised? What about when quantum computers become a real thing?
So actually, hashing is not susceptible to quantum computers because they cannot. It's a brute force. So I have actually to really compute this. I cannot reverse engineer it, but I have to try out all inputs, and quantum computers are not better in that. What you are referring to is the prime factorization. So this is used in private key cryptography, and this may one day become problematic if we use too short keys. So maybe like nowadays the keys which we use are too short, but if we make them much longer, it will be still safe for quantum computing. But so far the quantum computers are limited, and I talked actually to some physicists who are working on quantum computers, and they told me that it will take at least still 20 or 30 years until this will really becomes an issue. But actually Ethereum implements some methods, so it's possible to switch to quantum proof protocols. So they're already thinking about it for the future. So any more questions to hashing? Gabriela? No? Okay, so now you might ask, what does this have to do with the blockchain?
Who controls the hash rate controls everything.
Hashes are important. Okay, so let's clarify some just basic vocabulary first. That's first the wallet or the address, also called. They're used interchangeably, and the wallet is basically what we know as a bank account, and the address is like our IBAN in Europe, or the SWIFT code of our bank account, right? So it's just some number which can consist of numbers and characters, where we send our money, and then the bank knows this is our account, this money belongs to us. And with the wallet now in Ethereum and Bitcoin, it's pretty similar. So you have a wallet. A wallet it's like your bank account, and your address is your IBAN. So here on the presentation, I give you one example for Bitcoin. This is how a Bitcoin address looks like from the format here. So it's a very long combination of numbers and characters. And now the interesting thing is, now first connection comes in, this address is actually calculated from your public key. So when you create a new wallet, what you do is you find a random number, you create a public-private key pair, and then you can derive by your wallet address. So that means that to every wallet address there's a public key behind it.
So birthday paradox doesn't apply to.
So the birthday paradox, actually it applies also to collision, of course, to hash collisions. But even with the birthday paradox, these numbers, these probabilities are still so low. Okay, so since we can move along quite fast here, is this clear? Or you have some questions in the meantime? Just please ask, because like now is the chance. When you make a transaction now, so you have some. Let's stay with the example of Bitcoin for the moment. You have some Bitcoin in your wallet, okay, and you want to transfer some to your friends. So how does this work now? You have to send them a message, right? But you want not to only send him the message, but you want to send everybody the message that I transfer my Bitcoin to my friend. And the people now have to have some way of verifying that. So the message, of course, it has to include the amount, like how much you want to send, and the goal address, like with a normal transaction in your bank account, plus some other technical details which I will spare you for the moment. Maybe I can explain them to you later if you're very interested. So I create this message on my computer, okay, there's a special software for it, it's all specified in some protocols and rules how this message has to look like. And when I'm done, I sign it with my private key, right? So we talked about this before, because I want to send this message to other people, and I want them to be able to verify that, oh, this message comes really from this wallet now, from this address, so this address transfers money to someone else. And this is actually all that's behind the transaction. But now we have some problems. Do we have actually something to draw? No, I didn't think about that. Okay, no problem. I will just draw in the air, and you will think and you will see it. So since the blockchain is decentralized, so there is not a single entity that takes messages and confirms that. So, but everybody is basically one of these nodes and can verify that. There has to be some kind of understanding, like which messages are included, who owns what, like who did what happened. But everybody has to agree on the same things that happen. Because if I say, okay, you transfer, like there's always this example of the double spend, where I have one Bitcoin and I send it to two people. Since the network, the Bitcoin or the blockchain network, most of the time is decentralized, this means that it's a computer network of many computers. So for example, if I have one node here, and this is connected to one node here and one node here, and these are connected again to one node here and one node here, and at some point they meet, okay? And if I now send my message that says, okay, I send 1 Bitcoin to Alice, I send it to this node first, but at the same time I generate a message and says, okay, I send my 1 Bitcoin to Bob, and I send this message to the other node. So basically, because I know that they are not connected, or I can know that, I can find that out. So basically what I would do is, I would spend my Bitcoin 2 times. Very nice, right? I just doubled my money basically. And of course we don't want that, because if everybody does that, then it's useless. Nobody can use it because it's just useless. But this of course can happen because we're in a decentralized network. But now that the network, at some point, it has to agree either like was the money sent to Alice or was it sent to Bob? But they cannot agree that it was sent to both, because this doesn't comply with the rules of the protocol. So how is this done now? This is done actually by miners. So some nodes in this network, they're miners, and what they do is so they create blocks. So they get, if you want to send a transaction, they just send it out to all these nodes, and they communicate these messages, they forward them, and so on, so that it spreads in the whole network. It's like with the torrent network or BitTorrent, it's decentralized, and everybody downloads from someone, uploads something, and so on. But these miners now, they get the messages in, okay? And then what they do is they summarize multiple transactions. So a message is a transaction, that's what I wanted to say. They summarize multiple transactions to create a block. Just one nice block of multiple transactions, because if I have to always agree on the state of each transaction, and there are many transactions, it becomes a hassle. So it's easier to just agree on multiple transactions at once. And this is what's called the block time. So this is roughly every 10 minutes with Bitcoin. But how are these blocks now created? If miners could just create blocks and say, okay, this is a new block, we get this problem which I mentioned before in the history with the spamming. So like all miners could say, I found a block, I found a block, I found a block. So the question now becomes, okay, which one should we trust? Should we trust this block? Should we take this block as a state? And you again get some confusion because it's not clear what state really counts in the network. And now the hashing comes in. So miners take this block which they create, and then they take this information from this block as an input to the hashing function, and they create a hash. But they try to create not some hash only, but this hash needs to have a certain form. Remember what I said at the beginning, it's extremely difficult to find one hash, like exactly the same hash. You have to somehow change the input to arrive at the correct output which you want. And miners are actually doing that. So they have the block as input, but then they add a very small, for example, number. They can just count one. So they try to take this block plus 1, put it in the hash function, and they look what comes out. Then they take the block plus 2, take the hash function, and look what comes out, and so on. And what they're trying to find is not like one certain hash, but just a hash with a certain property. So in this case, that the first places in the hash are 0, for example. Right? So this is again statistics. If the alphabet is like all the 10 numbers and 26 characters, then you have 36 probabilities. And if you calculate, in theory, 36 different inputs, one of them will be a hash where the 0 is the first number. But you can play this game on, of course. So you can say, okay, the first 2 places have to be 0. Then the probability gets lower, of course, because it's 36 times, so 1 divided by 36 square, and so on. So it gets very fast. The number of tries you have to make increases, and the difficulty gets more difficult. And that's actually how all this mining works. So the miners, they only try to find this hash with certain properties. It's actually decided also by the protocol how many of these zeros are needed. So this is called the block difficulty. And in Bitcoin, we want the block to be 10 minutes long. But if now a lot more miners with more hashing power come in, then they will most likely find this hash faster, right? So the block time will decrease. and it's baked in the protocol that it will automatically make the difficulty more difficult, so that the block time stays around 10 minutes.
How often is it adjusted? You said automatically.
I don't know it from the top of my head, but it's not every block adjusted.
Yeah,
But
so there is a certain period. Let's say
I
2
think
days
it's
a week.
6 hours or 1
Yes.
week. I don't remember it honestly. I would have to look it up. But yes, basically they check off the period of time, a longer period of time, not only one block but multiple blocks. Then they take the average time and then they adjust it accordingly. But this is not done by people. This is done by the protocol, by the programs automatically. So there was a lot of information. Do you have some more questions?
I have a suggestion of actually how to trick the system and to make it overspend.
Okay.
But it assumes that you're a big player. Let's say you have a lot of computing power, not more than 50%, but a significant part of the computing power. So you're computing, right? For right now at point A, you're computing, and the difficulty is adjusted so that to meet the standard when you're computing. But then you retrieve, and so the computing power is much less. So the difficulty is adjusted. So the difficulty drops down, and then when you leave it for a certain period, and then when you join, no.
No, but if you
join, you can join when
and
the
your
difficulty is much
proportional
lower.
hash power will
Yeah.
get bigger.
It will be much bigger, and actually then you can start creating your own fork, as it's
But
called.
the idea is, so if this works really fast, but actually there's a lot of miners and a lot of blockchains right now.
Yeah,
If people
depending on the size of
if people
your
see
computing
that
power.
some like large pool went offline,
Yeah.
it becomes more profitable for them to mine Bitcoin themselves, for example. So that maybe some
So
people
then
will switch.
It will fix the market will fix itself.
Yes. So I mean it's actually quite valid. I haven't thought about. I think there is some attack related. I think you need 25% or so. There was some paper written about this. But yeah, so if you do this probably quick enough, it could happen, because it takes some time to add new computers and so on. But that's also why the block difficulty gets adjusted not so quickly, for this reason. Yeah, because otherwise you could find 2 blocks in 2 minutes, and then you increase the difficulty, it will take 30 minutes and so on.
But if it takes you 1 week and you are a huge factory, you don't want to be 1 week offline.
You don't need to be 1 week offline. You need
It
to be.
depends how long.
Yeah, you
Yeah,
need to
it
be
costs all of them,
consistent,
but
yeah.
it costs them all. So like actually the
Yeah,
question,
then-
I have to repeat the question. The question was what happens if someone with significant mining power mines and then decides to go offline of the network, and so that the key difficulty increases and then rejoins the network. So yeah, but
That's an option for a cartel to be made.
yeah, of course, so that there are actually these mining cartels. So it's called a mining pool. So I can show you actually how this would look like, something like that. You can see it on the screen. This is one miner, and yeah, they own a lot of computers. But still, if you would now mine with your own computer, you will probably never find a block because you don't have enough hash power. So you would go and join a pool, and then you get a small amount from each transaction, from each block that was found. Okay, so you can actually see also these blocks as an update to the state of the system, right? So the state of the system in the blockchain, in the Bitcoin, for example, would be like you have a list of accounts, and you know which account owns how much, right? So account A owns 2 Bitcoin, account B owns 3 Bitcoin, and so on. And so this is one state. Then you have one block, which is kind of an update to this state. So each 10 minutes there's like an update which says, okay, this changed, and this changed, and then you have the new state. And when you combine these updates, because you have to have all transactions every 10 minutes, you arrive at the blockchain. And each block, like I said, it contains all the transactions. It contains also some additional technical information, like the hash of the previous block, so that you can say which came first and which came next. And this nonce is actually this number, the solution to the hash problem. Do you have some more questions?
I have a question. We discussed it a few days ago about how miners create their nonces. Because as we discussed it, if you start creating 1, 2, 3, and it makes no sense because everyone else is making 1, 2, 3, and whoever makes them quicker is always going to win the race. So I think it's going to be helpful for the discussion if you tell how these nonces are created, how miners.
So the question was how are these nonces created? So I said before that you take a block plus 1 and plus 2 and plus 3 and you try all these possibilities. And actually it doesn't make sense. It doesn't matter now if I take the block and then plus 1 and the block and plus 2. I can also just use a random number or another sequence or whatever. It doesn't matter really. But additionally also it can actually happen that people are always mining on different blocks. So because the network is decentralized, so it means that not every message must arrive in time. So it can happen that I make a transaction, but someone is mining a block, and someone else is mining a block, depending on the last one, but they include different kinds of transactions. Because actually the miners, they can choose which they include. So
but is it possible, for example, to sabotage somebody? I mean,
to
if
sabotage.
you know what he's mining, can you mine it with your more powerful?
So what happens is when a hash is found that is according to the correct rules, the miner then propagates it as fast as he can to all the other people in the network, and they check then that this nonce or this small number really produces that output. And for them now they have to make an economic decision basically, and it's either do I ignore it and mine the old block new and then propagate my new because I think I will find it fast, or do I accept it and start mining on the next block? Because for them it's all about like what will the other people do? It's a bit of game theory, right? If everybody were to exclude, like just don't accept the blocks from this one miner, it would be fine. They could really censor them. And that's actually also the possibility which was mentioned of the 51% attack. So if you own more than 50% of the mining power, you can basically rewrite history. So blocks, the important thing is that always you have one block and then the next and the next. But what I said with these two transactions, it can also happen that two blocks are created at the same time and they then contain different state updates. But then the network has to come to a consensus, which it's called a fork actually, because before you have a chain, but when it splits you have a fork then, like a fork. And
so if you have more than 50%, you can actually manipulate the outcome.
If you have more than 50%, so what usually happens is maybe some part of the network thinks, okay, I got this block earlier, so I will mine on this block. And the other part of the network says, okay, because if they are at the same time, let's say one is created in China, one in the US, they propagate differently, and one part of the network thinks, okay, this is the one, and the other part thinks this is the one. But the assumption now is that it's never exactly 50 to 50%, because it's very unlikely again. And what happens? So let's say that one part of the network continues mining on this block, and the other part on the other block. So they both now have a different state of the world in the mine, basically. But at some point, one chain will be longer than the other, right? Because one part of the network has more mining power. And then if I'm at the shorter path, the shorter blockchain, I have to make again a decision. Like, should I continue here or should I maybe switch to the longer chain? And I mean, it's logical for the miner to switch to the longer chain, simply for the reason that this will probably be the chain that is accepted by all other people. Another 51% attack is you could create a longer chain, so this is accepted by everybody. But if you have 51%, you can at the side create a new chain, and at some point, after let's say hundreds of blocks, this becomes longer than the old one. and then everybody would switch to this one. So again, then you could rewrite the history, because at some point people thought these 100 blocks count, but if you have more mining power than the others, very slowly, but you will start to create a longer chain just at any point in the history. For now, to rewrite the blockchain, and so we have it today, we would need, with the mining power of today, still a couple of years to just come up with these hashes, hash after hash after hash.
But we can rewrite history only in certain constraints, right? Because you mentioned 100 blocks, so there is, as I know, there is a constraint on what is considered fixed in the blockchain, and you can never rewrite again. So you cannot go to the first transaction of Satoshi and then say, oh, this wasn't the Satoshi, this was the me. I mean, something is imprinted and stays.
So it's called finality, and actually there is no finality in blockchains per se.
There is no finality?
Well, there is just an agreed upon finality. Because if it's more, so if you go to an exchange and send the money, they will say, okay, when it arrives, we will credit it to your account and we will pay it out. But they will not say when we arrive the first block, but they say after 6 or after 10 blocks, or after some limit.
Okay.
And for them, then they consider it final.
Okay, so.
But in theory, you could, if you own 99.9% of the hash power, you can start speculating the first block and come up with a new chain. The question is then only, will the other people accept it? I mean, or is there...
What does it depend on, whether they will accept it or not, on the protocol, or?
No, I think that people would accept it because it's the longest chain.
It's part of the protocol, so it's a loophole in the protocol.
Of course, yeah. All this protocol depends upon that not more than 50% of hash power is owned by one single entity.
But you technically cannot own.
What about China?
What about China?
What about the percentage of China?
Yeah, so, okay, like I will come to this. Mining, well, I will come to that just to continue here. Okay, so we discussed this actually, and we discussed this. So yeah, right now the mining takes around, what did you say, Gabriela? 0.1% of the world energy consumption.
Yeah, 0.13%.
So I also.
And that's Bitcoin mining alone.
That's only Bitcoin mining. 0.1% of the world energy. So thousands. It's crazy. I mean, I found the statistics that it's the country of Iceland, but I think it's much larger already now. So again, you can see a nice Chinese guy, because they actually play a big role in the mining, and this is due to the reason that, so historically, when Satoshi Nakamoto invented the protocol, he said, okay, everybody will mine on his laptop computer, right, with his CPU, and it will be secure. If thousands of people will do it, fine. But of course, then there came some smart guys and say, oh, there's some money in that. I can also start mining with my GPU. But they wrote programs to run with graphic cards, and then they attached multiple graphic cards to each other, and then you're much more powerful than one CPU, like one CPU or one computer in the network. What the Chinese did, because they manufacture a lot of the electronics in the world, they came up with the first ASIC miner. So it's like dedicated hardware